Okay, in this problem, I've got a rod, it's got a elaborate loading here, and I'm trying to find the absolute maximum bending stress in this beam. So, what I need to do first is determine what is the maximum bending moment, okay, and where is it? So I'm going to do a bending moment diagram shown here. And the first thing I need to do in order to find that bending moment diagram is to determine my loadings at A and B, right? So I've got A over here and I've got B over here. Okay, so to sum the forces in the y direction, I have A plus B, and then I've got these two distributed loads acting straight downward. I've got the rectangular one, which is going to be 3 times 12. And then I've got the triangular one, which is going to be 1/2 times 1.5 times 12 equals 0. The other thing I've got, or the other thing I can do is take a moment equation. I'm going to sum the moments above B. It'll make my equation just a little bit easier. Okay, and when I do that, I'm going to have -3 times A. I'm going to have positive 1.5 times 3 times 12. That's for the distributed load acting right at the center. Then I've got a -1. This is the triangular one. It's going to be 1/3 of the way, so it's going to be 0.5. That is not a 5. 0.5 times 1/2 times 1.5 times 12. Again, that's the area of that equals 0. So that's two equations, two unknowns. From that, I can find that A equals 16.5 and B equals 28.5. Okay, so again, this one's 28.5 and this one is 16.5. Okay, so now I've got that, I can go ahead and start piecing together the internal moment, the moment diagram. I have to make two cuts here, right? Okay, so I'll start with that first cut, and I'll do it right below here. So I've got this cut here. Again, I've got 16.5 over here. I've got my distributed load, like so, and that's going to be 12. Again, I'm cutting it at some arbitrary distance x away. I've got a shear and a bending moment. And again, all I care about here is the bending moment, so I'm not even going to bother finding the shear on this. So I'm going to say the bending moment, or the summing the moments, again, I'm going to do about the cut point. That way the shear doesn't even show up. I want to include the bending moment I'm trying to find. And then we're going to have -16.5 times x for that reaction force over there. Then I've got my distributed load right here, which is going to be plus x over 2, 12x equals 0. And from that, I can determine that my moment equation is -6x squared plus 16.5x. Now, when I go through and plot that, okay, again, this is good from 0 to 3, okay, this guy's going to look something like this, okay. It's going to end at -4.5 down here, but look what happens. Okay, when I do that plot, I get a curve that looks something like this. Okay, and right here at this point, it's 11.34. That occurs at 1.375 meters over. It crosses over a 0 point right here at 2.75 for what it's worth. Okay, but most importantly, recognizing where that maximum occurs is going to help us determine where exactly the maximum moment is, and we'll see it is actually that point right there. So again, once you get your equation for that moment, you want to go through and make sure that the what that curve actually looks like. Don't always just assume one end is maximum, one is minimum, because this is not a straight line. It's a parabola that I've got to worry about. Okay, and again, had we done our shear diagram, at 1.375, the shear diagram actually goes to 0, which is a good way to tell, hey, I've got a local max or min there. So go and figure that out. Again, because the derivative equal to 0 means I've got a 0 slope. So just keep that in mind. I mean, we didn't actually calculate the shear, but if you do, that's a good way to see, okay, I've got a max that I've got to worry about here. Okay, but you can go ahead and plot that and prove that to yourself if you want. And there you have it. So now I've got the other cut that I've got to look at. Okay, where again I've got 16.5 right there. I've got my distributed load like so, and that's going to be 12. Then I've got basically it's going to be a trapezoid coming down like that. I've got a shear and a bending moment. That's what I'm trying to find, is that bending moment. This line right here, okay, can be defined as 12 minus 12 over 1.5. That's going to be the slope of that line, right? The rise is 12, the run is 1.5. Actually, the rise is negative 12. And then that's going to be x minus 3, right? Because x is the whole distance, and I'm just interested in what's going on after 3 in that piece right there. So that's basically the slope of that line that I've got there, okay, which is what I'm going to need in order to calculate that trapezoid, which I'm not very excited about doing. It's kind of long and tedious, and as we'll eventually figure out, wasn't exactly necessary to solve the problem, but we've got to prove it to ourselves, so we'll go ahead and go through with this. So from that, I'm going to go ahead and sum the moment. Again, I always do it around the cut point. Don't want to forget the moment at that cut point that I'm trying to find. But then, of course, I've got 16.5 times x in there. And then I've got my distributed load, which has the rectangular distributed load, which has 12 times 3, right? And then that's going to be times its location, which would be x minus 1.5. Okay, because again, the center of that is at 1.5. Okay, I'm coming from x because again, I'm doing from the cut side of the load. So that's where that 1.5 comes from. Okay, now, oh, I forgot one load here. I've got my 28.5. Got to remember that, right? That point load, that reaction load right there. So I'm going to include that. That's going to be negative 28.5 times x minus 3. Now I'm going to deal with the trapezoid, which I'm actually going to break up into two pieces. I'm going to break up into a rectangle and a triangle. So the rectangle, okay, has a distance of x minus 3, a width of x minus 3. Again, trying to do the area. This is going to be a positive moment. So x minus 3, okay. And then I need the height, which again depends on where I am on x, which is going to be that equation I just came up with, 12 minus 12 over 1.5 times x minus 3. Okay. Now I need the location, which is going to be the midpoint of that x minus 3 piece. So that'll be x minus 3 over 2. Okay. Now I've got the final piece, which is that small triangle. Again, kind of what I'm looking at is I'm breaking that into two pieces like that. So that final one, the area is 1/2, and then x minus 3, which is the base, and the height of this guy is going to be 12 minus, I'm sorry, not 12 minus, 12 over 1.5 times x minus 3. And again, it's not the 12 minus that, okay, because again, at one end, it's going to be, what would it, well, I guess it depends on what x actually is, okay? And then the location of that is actually 2/3 of the way from the x minus 2, because again, it's from the pointed side of the triangle like that. Okay, very, very tedious, very lots going on there again, but basically I've got 2 point loads, the reactions. I've got that whole rectangular load, and then I've got this trapezoid, which depends on the length of x, which gets me to an actual quadratic when I do this. And I see that the moment, again, the equation for the moment, this will be from 3 to 4.5 meters, then becomes, when I simplify the equation, 4/3 x cubed minus 13.5 x squared plus 60.75x minus 91.125. And again, it is just that kind of tedious equation, simplifying that out. Again, I've got that sliver of a triangle depends on x. I've got the smaller rectangle that depends on x as well, which makes things actually work out to be a quadratic. But now that I have that, I can finish my equation. I know it's going to end at 0, and you can prove that to yourself by plugging in 4.5 there. And this guy follows a plot something like this. So again, this guy right here, this is my maximum moment, which is what I needed to find here. Okay, so now that I have that maximum moment, now I can easily find from my Flexure formula, which again is mc over I. Okay, I have that, and that's going to be 11.34 kips, or 11,344 pounds. Okay, times c, which this has a diameter of 90 meters. The radius then is 45 millimeters. Okay, and then I, for a circle, which is what this is pi over 4 times 0.045 to the fourth. Okay, and that's just I about this point. Okay, so again, the maximum moment is going to occur at the edge. That's why I use the radius. Okay, I, this is a symmetrical thing, so I is just pi over 4 times the radius to the fourth. The real tricky part here was finding that maximum moment, which is a little tedious, but we found it to be 11,000 pounds. Plugging, not pounds, excuse me, newtons. I was saying kips. I meant kilonewtons and newtons. From all of that, I find 158.5 megapascals. Okay, so again, trick here is that bending moment diagram to figure out exactly where the maximum moment is. Once I have that, then the Flexure formula is not actually too difficult. The key is determining, using the bending moment diagram, exactly where that maximum moment is.